Okay, hi everyone. So we're very happy to have the second talk for today in the morning session by Christian Blanchet from Université Paris, who is going to tell us about Heisenberg homology of surface configurations. Christian?
Okay, thank you. So I guess some people are still ordering. I will start slowly. Okay, I should have. Okay, it's better. Okay, so my talk will be on certain homologies of surface configuration, but the slogan is, can you recover quantum stuff, maybe quantum invariant or quantum representation, from classical algebraic topology on those configuration spaces. And I should say that this is based on a common work with Martin Palmer and Avais Chocat. And we are trying to go further with an ongoing project with Anna. So as a motivation, just a few words about what is called, what was at the beginning a Lorentz representation. And she gave families of representation of the classical braid groups acting on a certain homology. And here, I guess everybody knows about classical braid group, but this dm is just a punctured disk, is a d2 minus m points. So I can draw like this. And then we consider configuration. So in this punctured disk, meaning that you add, first the pi1 of this is the classical braid group. And when you represent a braid, when you take an element of pi1, this is a loop in the configuration. So configuration is a set, finite set of distinct points inside this punctured disk. Then first pi1, so Bm, pi1 of D2. Oh, I'm sorry. I'm sorry. I want to say too much. Sorry. Let's go a little bit. Yeah. 1 minute. Okay, let's go further. I will give for surfaces. So we are working with this representation. So here, this Cn tilde of D2m are a configuration in this disk. So you take, for example, 2 points, and you I'm confused, I'm sorry. Yeah. This Cn tilde of dm is included in. I'm sorry, I was thinking in the meantime with surface and disk, and I'm not clear in my mind. I'm sorry. Of dm, sorry, n points here to the n. And here I ask that the points are different, just this. So I'm okay with this. Sorry? dm, yeah, sure. So I'm okay. Okay, so then I'm interested in, sorry. For the moment, it's not a cover. So it's not the usual braid group, but I can consider this guy. with a certain base configuration. So this guy is a kind of braid group, but not the classical one. This is something which will be included in the braid group with m plus n points. So the classical braid group. So you have the blue points which are not moving, and you have the green part which are moving. And from this, if you take an homomorphism from, for example, Z2, and this you can do by abelianization, the kernel of this homomorphism will allow to build a covering space for this Cn of dm. And you can study the homology of this covering space. Consider, if you want, two parameters, so that you have an abelian local system on new configuration space. And this Lorentz representation is action of this homology with local coefficient. And so this was a famous theorem by Bigelow and Kramer in 2000-something, independently, that with n equal 2, this L2 is faithful, and taking two generic transcendental real parameters, you get linearity of the classical braid group. So that was the situation. And so it is known that this representation are related with quantum. Indeed, Kono showed that this representation, whatever it is exactly, whatever are the formula, are equivalent to SL2 quantum representation on certain highest weight spaces. So you start in genus 0 for the disk with classical algebraic topology. Then you have action of the classical braid group, and you recover certain quantum stuff. So now we observe that this classical braid group is a mapping class group in genus 0. So by mapping class group here, we take diffeomorphism of the disk which are identity on the boundary, and we take this up to isotopy. And it's easy to see that the classical braid group can be also defined as this mapping class group. So the question now is, because it was first by Lorentz but used by Bigelow and Kramer, this representation are often called LKB representation. And the purpose is to try to extend the method in order to get a representation of the higher genus mapping class groups. And this is our goal, to get the same type of representation for the mapping class group in higher genus. For technical reason, we stay with surfaces with one boundary component. This is just easier to compute and more comfortable, but we have also definition in other cases. It's easy when we have at least one boundary component, but it can also be done for closed surfaces in a more sophisticated way. So for this construction, in fact, here the local systems were coming from abelianization, and it happens, and that's why it took a while, that abelianization of the appropriate pi 1, which will play the role here for constructing local system, this abelianization, it's almost the same as the homology of the surface. You get nothing really strongly new, and we will see later, by taking abelianization. Then we are pleased to consider the idea, the key idea here, is to replace the homology of the surface by the Heisenberg group. So in the Heisenberg group, you add a central parameter. For physicists, this is used with the central charge, I guess. And the formal definition is, say, take a central extension of the H1 of the surface using the intersection co-cycle. You have intersection of curves with signs, which give a symplectic structure on H1 of sigma. And then you define this extension, and formally you get Z times H1, so an integer an homology class, but the product is corrected with this x dot y, which count the intersection of the two homology classes. So this is a non-commutative group, but this is non-commutative, which is the closest as possible to commutative. So then our result is to observe that there is a quotient map from the surface braid group, so the pi1 of configuration in sigma, to this Heisenberg group. And so the general idea is when you have a nice representation of pi1, this gives you a local system. Whatever you think about for the local system, if you are more geometers, then you will get a flat connection if you want. Else, you say, yeah, we have a quotient. We can play with the universal covering and tensor product with the representation. And then, this is what we say here. If we take a representation of the Heisenberg group, and we know some nice ones, then we also have a representation of pi1 of configuration, and this will give you a local system, hence an homology theory. And the question is, can we study this group and the corresponding possible mapping class group action? On the nose, it will be a twisted representation, for the reason I will explain. And then the next step is to say, take Q as a parameter, and this Q will be the central charge, the action of the central generator of this Heisenberg group. And for this talk, I will keep this Q to be a root of unity in order to get finite dimensional representation. But the Hilbert case could be also considered. We keep this in mind.
Can I ask a quick question?
Yes, sure.
Is this naturally show up in terms of conformal blocks or something? Is it bundles?
I will come to this. Yeah. The answer is we can recover certain kind of conformal blocks in one case using Schrödinger representation.
I see.
Yeah, the answer will be yes. Thank you for this good question. So this is just for motivating those who are interested with conformal blocks. Yeah. So the question would be, I said quantum, but the question is similar. Is there an algebraic topology approach to certain conformal blocks? Oh, sorry. So then, if this Q is a root of unity, and I will restrict to odd root of unity in this talk, but we can extend. We specialize to a Schrödinger representation of this Heisenberg group. I will sketch the definition. And then we obtain projective. The important is that we get unitary representation of the mapping class group. The fact that it is projective is that the representation will be given up to an element of S1. But this is not a big deal because you can take a central extension of the mapping class group and get a native unitary representation of the mapping class group. This is the goal. So then we start with a surface braid group. Okay. And this is just a pi1 as before of the configuration. So it's the space of n distinct points just in the surface, no point removed for the moment. That's what I was confused at the beginning. and the sigma has one boundary component. So then this braid group has a presentation. So we don't need to understand everything in the presentation. We just need to know that this is understood. What is interesting is to think about the generators. So if, for example, here, think that I just add an handle and get a band. And I'm working with configuration of 2 points. So I remove this. And I'm working with configuration of 2 points. One thing I can do is braid, classical braid of the 2 points. So this will be responsible for sigma 1. And when I have this braid, I used to draw the graph in the surface times interval. So from here, I will get, so I have interval, and the sigma 1 will be like this. So this is sigma 1. So you just think this disk times interval going up, and you follow the path in the configuration. So this is one thing, but I could also consider another one, which is, so then I say here that I will get all the classical generators sigma 1 to sigma n minus 1. But then what I can do also is keep only move one strand. And this one can go here. Maybe it's better in the other way, whatever. And then come here. So along the way, we use an element of pi 1, just on the first strand. So I say that we will have classical generator and pi 1 generator. You take your preferred pi 1 generator, and that's it. You have the generators. Oops. Sorry. Yeah. So you see this bunch of relation, and I just point you the last one. Why about the last one? Because it's clearly not homogeneous. And so if you abelianize this last one, you will get sigma 1 square equal 1. And this is what I meant by the fact that if you are brutal and take abelianization, then you will have something which is not really stronger than taking homology of the surface. But you see that if you Q commute, then that's fine. And this is a statement that so I already gave the definition of the Heisenberg group with its product. I remind this. This is important. And remember this last relation. It will be satisfied in the Heisenberg group with sigma 1 generic, with no relation on sigma 1. And from the presentation, what we get is a quotient map isomorphic to, with image isomorphic to the Heisenberg group, where sigma 1 becomes central, but the group is not commutative. You have a Q commutation for this, yeah. My quotient is all commutators between the group, the normal group generated by all commutators of sigma 1 with anybody. But the idea is just make sigma 1 central and take the quotient group. Okay? We even have an explicit isomorphism where we send Na sigma I to the central generator, U equal 1, 0. Just ask question if this is not clear. Then the pi 1 generators are sent to lifts in Heisenberg of the corresponding homology classes. And then that's it. We have this quotient map. The AI is the homology class with the tilde is a preferred lift in the Heisenberg group. But we should be careful that if you multiply AI tilde with BI tilde, you will get AI plus BI as a second parameter, but a 1 in the first, in the central charge, because of the intersection of AI with BI. It's Heisenberg. So now, okay, so, yeah, it's interesting to understand how this mapping class group is acting on Heisenberg, because this will be responsible for a map on the local coefficient, for an isomorphism on the local coefficient, for a twisting. So for F, a mapping class, so represented by a diffeomorphism, you can take the corresponding map at the level of the configuration. F is acting also of cardinality n subsets on configurations. And then we claim that we have an induced map on the automorphism of the Heisenberg group. Well, you have Heisenberg groups, you have automorphism of the Heisenberg group as a group, and I put a plus for the automorphism which are identity on the center. So U give U, and that in our case we know we can check that U give U. I'm quick. This automorphism group has a map to the symplectic group, but you have a kernel. So you have this automorphism of H, then you go to the SP of H, and this map is surjective. But here you have a kernel, here, and this kernel can be identified with H1 of sigma gamma Z, the dual of the lower homology, and moreover, here you have a section. So we get a semi-direct product structure. And so here there is a small subtlety, because the symplectic group is also acting on the Heisenberg group via this section, but the induced action in my construction is slightly different, because we have a correction at the level of the kernel. And this is what I write in here. So this is a little bit an aside. I will come back later to the homology, but this is an interesting aside that if I take this action of a mapping class on the Heisenberg group, I will send K central part to X, to, of course, F star of X at the level of homology, but K plus a correction at the level of the center. And this correction is interesting guy. It has natural property. This is for people more involved in maybe homology of groups. This is a crossed homomorphism, meaning the formula I gave here, it's not an homomorphism on the mapping class group. It's easy to check. And this crossed homomorphism play a role in cohomology of groups, and Morita proved that this guy generates the one-dimensional cohomology of the mapping class group with coefficient in the one-dimensional cohomology. This means that the fact that it's not the symplectic action is highly non-trivial, because the difference is not only a function. It's a function whose cohomology class, in certain sense, is highly non-trivial. Okay, this was parenthesis. So now we have this, we denote by Cn tilde the regular cover associated to the kernel of this quotient map, and call it the Heisenberg cover of surface configuration. This is the analogous guide to the Cn tilde before. Then we take the chain complex of this Heisenberg cover, whatever theory you like. It could be singular chain complex or cellular chain complex if you manage to do this. For certain theory, it's better to take cellular because you will get finite. However, with certain, yeah. And so it gets an action by deck transformation. And because I'm writing composition from the right, it's a right action of the group ring of the Heisenberg group. So then, if I have a representation of Heisenberg of sigma, the corresponding local homology can be obtained by tensoring with the representation. But if you have other model from flat connection or something, this is the same. This is that as a topologist, I like this model. So you take your favorite complex for the configuration, and you tensor product with the representation. So we have an homology theory. So the question is to compute, and but we will first talk about, we know to compute some, but we first talk about the action of mapping classes. Okay. So if I have a mapping class represented by the diffeomorphism G, here I use a different notation for the map and its class, then the Cn of G lifts to the Heisenberg cover. This is because this respects the kernel of the quotient map. We know explicitly this kernel of the quotient map is generated by all commutators with sigma 1. So we can check that this lift exists. And this induces a chain map by functoriality. However, so this chain map will be Z-linear if we are starting with a complex of a Z. But with respect to Heisenberg action, it will be a twisted linear. Because we saw that the mapping class is acting on the Heisenberg group. So we get something which is twisted linear. And this is the formula. If I act on the right by ZH, sorry, the parenthesis is not very good. You should think that ZH is an action. So ZH is an element of, yeah, no, Z, sorry. H is acting on Z. Z is a chain. And then we can act on, we can take the image of the chain Z, but act with the twisted element of the Heisenberg group. So you should think a while that you have this chain complex of the covering space. This is a native group, abelian group, with Z coefficient. So if you have a map, you have the Z functoriality, but you want to see, using this functoriality, how it works with the extra action of the Heisenberg group. And the question, the answer is, it can be managed, but with a twisting of the action. And this is important for the local system. So we get, in fact, using the local systems, if we have a representation V, we have a modification, a twisting of the coefficient. And you can check that the natural homology map goes from twisted coefficient to the original coefficient. Here, if the representation is rho, so this rho is going, so you have the Heisenberg group, you go to GL of V by a certain representation rho, but here you can precompose with an automorphism, let's say FH, or it can be a tau, and then you have the composed representation, and the space with this action, so this is the action FH rho, and when you are using this action, rho, and here this is, we get a map from H to GL of what we will denote FHV. V twisted by FH. This is a notation. So you think that we understand what happens at the level of the coefficient. And then, so I have to talk a bit about some variance. Okay, so I will use what is called the Borel-Moore homology. So this is similar to the homology using locally finite chains. And then it can be defined as a limit of a complement of compact subspace. And this is very appropriate when you have a non-compact manifold. And here, configuration, because points can become very near, you can go very near the diagonal in the symmetric space. We have a non-compact space, so it's appropriate to consider this variant. And then this Borel-Moore homology is functorial with respect to proper maps, in the sense that the inverse image of a compact is a compact. And we have also a relative Borel-Moore homology, and we will need, for the computation, a relative Borel-Moore homology in this context. So then, the configuration denoted sigma boundary. So my sigma now, I gave a model. So I decompose the boundary of sigma in two parts. So I will have boundary minus of sigma, and then I'm gluing handles like this. So this will be boundary plus of sigma. And then what I denote Cn, okay. Cn of sigma, boundary minus of sigma, is a subspace where configuration have at least one point in the blue part. Okay. And then, so this is my model. And what is, now I will say something about certain cycles. At the end, in a moment, I will need to give a description of the homology I'm defining. And here I put the gamma I as the cause of these handles. These are arcs inside the surface. And if I take 2 points, I can put 1 point moving on gamma 1 and the second point moving on gamma 2. What I will get is a square. Intervals times interval. And what I say is that this square represents a relative cycle in C2 sigma, comma, C2 sigma boundary minus. Because the boundary, if I take the boundary of the square, I will always have 1 point on the blue part. So I should understand that a lift of this square in the coverage space is a 2 cycle. So you see, my goal is to say from the combinatorics associated to this model surface, I will describe a basis of certain homology. So the second cycle, which I can do, is not use 2 arcs, but put just a configuration of 2 points on gamma 1. So then I'm going to infinity, because these 2 points can be very close. But if I'm working in Borel-Moore homology, this will still represent a 2 cycle in the Borel-Moore homology. And so the next result will be, if I take my n and take all partition of n in 2G parts, I will get a nice collection of cycles, and the theorem is that they represent a basis. And this can be done. Okay, so this is the theorem. If n is greater than 2, G greater than 1, V a representation of the discrete Heisenberg group of a ring R, then this Borel-Moore relative module with coefficient in the representation V is isomorphic to the direct sum corresponding to the number of partitions of n in 2G parts. And I know an explicit description of the basis. So I have a complete description of a version of this Heisenberg homology. And furthermore, it is the only non-vanishing module in this version. It's also interesting to compute non-Borel-Moore version or absolute version, but it's much harder. So I can give model, but not full computation. But this one is nice. So again, let's summarize. We started with configuration on surface, understood that the Heisenberg group is a covering space, is a quotient map of the pi1. Then we can, with the representation of Heisenberg, get a nice local system, define certain homology, and there is some variant we can compute explicitly. Now, what about the mapping class group? So just from scratch, from functoriality, we get a twisted representation of the mapping class group on the R modules, which are given by those homologies. We know that these are 3 R modules. I can vary the twisting. I like to vary the twisting. So if I take coefficient, the representation V twisted by n tau, then the functorial map will go with coefficient tau composed with fh to twisted by tau. So I like to write like this because then I see the twisted representation as a functor on a certain category whose objects are automorphism of H. Again, for representation, so this I gave you. V tau is the twisted one, as written here. And this theorem can be formulated as a functor on a groupoid whose objects are automorphism of H, and morphism are compatible mapping classes. Okay? So for the moment, we have a nice formulation of a twisted representation. So how much time I get? 5 minutes. Okay, that's fine. So now we go to the Schrödinger representation. So I start with P, an odd integer. Then the Heisenberg algebra, we can take an appropriate finite quotient HP of sigma, where I take ZP times H mod P, and try to represent this. For Q, a P root of unity, HP of sigma act on a finite dimensional Hilbert space. I will give the formula. It's finite dimensional, so it's a unitary action, but on a finite dimension. It's not a full Hilbert space yet. But in case I give the formula in genus 1, in case J equal 1, H1 of sigma has basis meridian longitude with intersection 1, and we have all elements of HP of sigma as K xm plus YL with coefficient in ZP. And this W Q will have basis BI, I in ZP, with action, central action Q. The longitude will act by translation of the index in the basis. And the meridian will act by, we say, modulation. And this is a standard scheme for Schrödinger representation. And we have similar formula in higher genus. So then, in the finite case, you have easily this Stone-von Neumann theorem saying that WQ is an irreducible representation of this finite Heisenberg group, and up to unitary isomorphism, it is unique, provided we act by this central character. Meaning that when we twist this W, we get isomorphic coefficient thing. Then, I just mentioned that Gelka and Korozov worked on the even case on this theorem, and we can also work out the even case. For P2 mod 4, there are subtleties, but let's. So then, this Stone-von Neumann theorem provides a unitary isomorphism, as I said. This means that before, when we did not have an endomorphism, now, using this isomorphism of coefficient, we get an automorphism. And the statement is that we get projective representation, unitary projective representation of the mapping class group on those homologies. And if we go to a central extension, we have unitary representation, native unitary representation of central extension. So now, about quantum. So our young colleagues Marco de Renchi and Jules Martel, they recently proved the following. First, there is an action of the small quantum SL2 on the sum of those homologies, which is very interesting. Second, if you take this, you are at a P root of unity, you can take a truncated sum only, and inside this truncated sum, you get a sub-representation, which is G times the power of the adjoint representation of the quantum group. For G equal 1, you recover the adjoint representation, and this is very interesting. And not only it's you get this quantum stuff, but it is known that some version of non-semi-simple TQFT first constructed by quantum representation first constructed by Lyubashenko are acting, give a representation of the mapping class group on this tensor product. And they proved that they constructed an isomorphism which intertwine the action of the quantum group and the action of the mapping class group. So indeed, this construction recovers certain TQFT representation. So now I will finish, this is the last one, with action of cobordism, because that was in the title of this conference. So I will finish with this. So we have homological construction of representation of mapping class group, which were previously quantum representation. The question is, do we extend to cobordism? In fact, the Schrödinger representation can be defined and fixed using a Lagrangian subspace in H1. So a G-dimensional thing where the intersection is 0. And then a cobordism will provide what we call a Lagrangian correspondence, meaning a Lagrangian in the homology of the union of the surface, which is the entrance of the cobordism, and the surface, which is the output. Okay, the picture is that you have our surface is with boundary, so you can construct a cobordism C, and if you consider the surface, which is the gluing, you have a natural Lagrangian here. And then what we prove with Anna is that this Lagrangian correspondence is acting on the Schrödinger local system. So the meaning of this, so this is, I wrote this as a tensor product over the Heisenberg algebra of the entire surface. The fact is that the Schrödinger representation associated with the Lagrangian correspondence is a bimodule over the two Heisenberg algebra. So it's an action by bimodule. And so using this, so this means that we get an action of cobordism on the Schrödinger local systems. And now the question are, can we understand natural action of cobordism on the previously defined Schrödinger homology? I call Schrödinger homologies the Heisenberg type homologies for this specialization, for this Heisenberg representation. And the next interesting question is how much could we do this if we are working with a generic Schrödinger representation? Is there something in the infinite dimensional Hilbert case? Thank you so much.
Further questions, Christian? Me too.
Yeah, can you go back 2 slides?
Okay.
Where you had the formula. There, yeah. You have this result, first bullet point, there's an action, a small SL2 quantum group on the sum. Is that sum categorifying anything if I take the graded character of that sum?
The answer is that at the moment I don't know, but this is one purpose of this program, to have models where you have a chance to categorify. In fact, it depends on your culture, but what I observe here is that the cycles I've described are Lagrangian cycles in this symplectic situation. So if you know about Fleur-Fukaya stuff, then you have some hope. Or if you are aware about mirror symmetry, you can expect to work more algebraically on the other side of the mirror symmetry. So the answer is at the moment no, but it could be some indications that such program could go. Thank you for the good question.
Okay, any other questions? Okay, if not, let's thank Christian again for the very nice talk. Thank you, Christian.